In this video, we're going to go through mole concept and chemical calculations in the A-level syllabus. When we go through the learning outcomes, it appears as if we have already learned everything in the O-level syllabus. So what exactly is new in the A-level syllabus is that we learn to apply what we have already known to more advanced types of questions. And for each type of such questions, there's a specific approach or strategy to solving them. So in the A-level syllabus, we'll be looking at these approaches and strategies to solving specific types of advanced questions. Before we even go on, I cannot stress enough that you need to have a very solid foundation of mole concept and chemical calculations of your O-level syllabus before we can even move on to looking at these advanced questions. Here are some of the topics that we have already learned in the O-level syllabus, and again, it's very important for you to already have a very good understanding of the concepts in there. Otherwise, I would suggest that you watch the videos for your O-level mole concept and chemical calculations first before coming back to this video. In the A-level syllabus, essentially, we are looking at three new types of questions: more advanced titration questions, combustion analysis, and reacting mixtures. So in this video, we're going to focus on the first type, which is the more advanced titration concepts and questions. For titration questions, two very important phenomena that you need to be aware of are dilution and sampling. So if we read the procedure given in the question, the first line involves adding water to 10 centimeter cube of an acid to make it up into 100 centimeter cube. So we are adding water to acid. Essentially, we are diluting the acid. So step number one is a dilution process. Now, a standard flask is also known as a volumetric flask. What is it used for is similar to a pipette. It is used to measure accurately a fixed volume of liquid. So what happens if you add water into a standard flask until it reaches the mark? The mark is a thin line which is very similar to what you see in a pipette. So if you add water until the solution reaches that line, it means that you have prepared that volume of solution. So for example, if you add water into a 100 centimeter cube volumetric flask until it reaches the line, it means that you have prepared 100 centimeter cube of solution. In the next sentence, from the 100 centimeter cube of solution P, we take out 25 centimeter cube of the solution. All right, so we are only taking out a small portion. We are sampling the solution P. So sentence 2 essentially represents the phenomenon of sampling. Now that we have learned to identify dilution and sampling, we must know certain very important concepts associated to the two processes. Now, when we add water to dilute a solution, the important thing to remember is this: because we are adding water to a reagent, all right, essentially the number of moles of your reagent do not change. Okay, or in this case, the number of moles of acid do not change when we add water to the acid. Okay, however, the concentration will be lesser when we add more and more water. Now, based on the fact that the number of moles of acid remains the same, so before and after dilution, it remains the same, we can actually derive a very important equation, which is this. Concentration, C stands for concentration, V stands for volume, I stands for initial, and F stands for final. So the concentration of the initial solution, or the initial concentration times the initial volume, is equals to the final concentration times the final volume. Now next for sampling, essentially we are taking a small fraction of a solution. So when you perform sampling, since you are taking only a small portion or fraction of it, your number of moles will change. Okay, the number of moles in the sample will only be a fraction of the total amount. However, the concentration will remain the same. Now, based on this fact that the concentration before and after sampling remains the same, again we can derive a very important equation, which is this, that the number of moles of reagent in the sample divided by the volume of the sample is equals to the total number of moles of reagent in the original solution divided by the total volume in the original solution. Now, one easy way to remember dilution and sampling is by using this analogy. So imagine that I add 2 tablespoons of Milo powder into 10 centimeter cube of water. So right now I have a very concentrated Milo solution, and when I add more water to it to make it into 1000 centimeter cube, essentially I'm performing a dilution. So after adding the water, would the Milo taste the same? The answer is obviously not. So the concentration represents the taste. It will be much more dilute, all right? But is the amount of Milo powder the same? Yes, it is still 2 tablespoons of Milo powder. So the number of moles don't change when you perform a dilution. Now imagine that I now have this 1000 centimeter cube dilute Milo solution, and I pour out a small cup of it, 25 centimeter cube of it, all right? Would the amount of Milo powder in this 25 centimeter cube of Milo solution be the same? Would it be 2 tablespoons? Answer is no, because this small cup of Milo only represents a fraction of the total solution. However, will the taste be the same as the total solution? The answer is yes. So the concentration of your solution when you perform a sampling do not change. So right now I'm going to use the concepts that we have learned to apply it to this question over here. I'm going to solve it in 2 slightly different ways to illustrate the concepts of dilution and sampling again. Now to solve this question, essentially we can use our familiar 3C approach. First C is to convert to moles, so we find number of moles of sodium hydroxide. Second C is to compare mole ratio. We need to compare mole ratio between the hydrogen ions and your sodium hydroxide. So in a reaction like this, the ratio is 1:1. So meaning the number of moles of hydrogen ions is equal to number of moles of sodium hydroxide, which is 2 times 10 to the power of minus 3 moles. Okay. However, remember there is sampling involved. So in the titration, we took out 25 centimeter cube of solution P from a total of 100 centimeter cube. So the number of moles of hydrogen ions that we have found is only in 25 centimeter cube of P. And since the question wants the concentration of hydrogen ions in the original acid, we need to find the number of moles in the total 100 centimeter cube of solution P. And how do we do that is to make use of the equation that we have seen involved in sampling. So based on this equation, we can find that the number of moles in the total solution P is actually 100, which is the total volume, divided by 25, which is the volume of the sample, times the number of moles of hydrogen ions in the sample. So that will give us 8 times 10 to the power of minus 3. This represents the number of moles of hydrogen ions in the total 100 centimeter cube of P. Next, we can find the number of moles of hydrogen ions in the acid, okay, meaning before dilution. So this is where an important concept of dilution comes in, that when you perform a dilution, okay, the number of moles of your reagent don't change. So the number of moles of H plus in that concentrated acid is actually equal to the number of moles of H plus in your solution P. So it's equals to 8 times 10 to the power of minus 3. and therefore the concentration of your acid or H plus in the original acid is just number of moles divided by volume, volume being 10 centimeter cube, which will give us a concentration of 0.8 moles per dm cube. Now I'm going to solve it slightly differently, again to showcase some other important aspects of dilution and sampling. The first step is the same, to find number of moles of sodium hydroxide, and then by comparing mole ratio, I can find the number of moles of hydrogen ions in 25 centimeter cube or in the sample of P. Similarly, since we know that there's sampling involved, we need to find the number of moles of H plus in the total solution of P. Okay, so in this working, what I'm going to do is I'm going to find the concentration of H plus in solution P first. So I'm going to divide the number of moles by the volume of P, which is 100 centimeter cube, which will give me a concentration of 0.08 moles per dm cube. However, it's important for you to recognize now that this is the concentration of hydrogen ions after dilution. Okay, so how do we find the concentration of H plus in the original 10 centimeter cube of acid? Is to make use of this equation over here. So given the final concentration of acid, the final volume and the initial volume, we can actually find the initial concentration, which is just 0.8. One concept that you may find useful is the concept of dilution factor. What is dilution factor? Dilution factor is VF over VI. Okay, so for example, in this particular case, dilution factor is 10. It means that the solution has been diluted 10 times. So to find the concentration of hydrogen ions in the original acid, we just need to times 10. The next type of titration question that we're going to look at is known as consecutive reactions. Now, conventional titration reactions only involve one reaction, a reaction between an acid and an alkali, or between an oxidizing agent and a reducing agent. However, there are some titrations where what we want to find is not directly involved in the titration itself. So for example, in this case, we want to find the number of moles or the amount of copper 2 ions. So we first add excess potassium iodide to generate iodine, and then we titrate the iodine with sodium thiosulfate. Now, to solve questions like this, we can also just simply apply the 3C approach 2 times. For example, we'll first find number of moles of sodium thiosulfate, and then by comparing mole ratio, we can find number of moles of iodine. And once we know the number of moles of iodine, again we can compare mole ratio to find the number of moles of your copper 2 ions. Okay. However, for consecutive reactions, there is a shortcut, and the shortcut is to compare directly what we want to find versus what we get from the titration. So for example, if we just look at the ratio of thiosulfate with iodine, it's actually 2:1. And then the ratio of iodine to copper 2 ions is actually 1:2. So if we simply compare sodium thiosulfate to copper 2 ions, the reacting ratio is essentially just 1:1. So if we read the question on this slide, we are required to make use of the titration data to find the percentage by mass of copper in a screw. And once we have taken note of the reacting ratio between sodium thiosulfate and copper 2 ions being 1:1, we can essentially just solve it in a one-step 3C approach. So firstly, we find number of moles of sodium thiosulfate, and then by comparing mole ratio between sodium thiosulfate and copper 2 ions, which is 1:1, we can find number of moles of copper 2 ions. Now, if you read the procedure carefully, I hope you have detected that there's sampling involved. So the number of moles of copper 2 ions found in the titration only represents a fraction or a sample of your solution Q. since we need to find the mass of copper in the screw, we need to find the total number of moles of copper 2 ions. So we need to apply the sampling formula, all right, to find the total number of moles of copper 2 ions in the entire 1000 centimeter cube of solution Q. Once we have found the total amount of copper 2 ions, we can find the mass by multiplying it by molar mass, and then later on to find the mass percent of copper in the screw. The next type of question that we're going to look at is known as a back titration question. Back titration also is known as indirect titration. Is used when the substance that we want to find the number of moles for, or the amount of, cannot be used directly in a titration, in a conventional titration. In a titration, the two reactants must be in solution form in order for a titration to work. However, for let's say if we want to find the amount of an insoluble solid, then we can no longer use a direct titration. However, in this case, we can still use what we call an indirect titration, and the concept goes like this. And a back titration would involve three reactants. Reactant A is the one for which we want to find the amount of. So for example, if we want to find the amount of calcium carbonate in a seashell. Now calcium carbonate is insoluble in water, so there's no way for us to dissolve it to do a titration. So what we can do is to react your calcium carbonate with a second reagent, in this case hydrochloric acid, and we add excess of the acid. So what's going to happen is that after the reaction, your acid is going to react away all your calcium carbonate. Okay, but being added in excess, there will be some remaining after the reaction, and then we are going to we're going to titrate this remaining acid with a third reagent, in this case sodium hydroxide. So the trick to solving a back titration question is uncannily suggested by the name, is to work backwards. So the first thing that we can do is to find number of moles of sodium hydroxide, okay, from the titration data or the titer value. And by comparing mole ratio, we can actually find number 2, which is the number of moles of acid that was remaining after the first reaction. And in the question, they will give you the total number of moles of acid that was added. So from the total number of moles, we can find the number of moles of acid that had reacted with my carbonate, okay, which is represented by number 3. And then by comparing mole ratio once more, I can now find the number of moles of calcium carbonate that was present. So let us take a look at an example now. So as mentioned, in any back titration, there are 3 reagents. The first reagent over here, reagent A, is your calcium carbonate. Reagent B is your hydrochloric acid. And then reagent C is your sodium hydroxide. So as mentioned, the trick to solving a back titration question is to work backwards. So first we find number of moles of sodium hydroxide from the titration data. Next, we compare mole ratio to find the number of moles of acid that was remaining after the reaction. So how do we compare mole ratio? In this case, we are titrating hydrochloric acid with sodium hydroxide. So the reacting ratio here is 1:1. After finding the number of moles of acid that was remaining after the first reaction, we can then go on to find the number of moles of acid that had reacted with calcium carbonate. And how do we find that? Is to take the total number of moles of acid, again this is given in the question, minus the number of moles of acid that was remaining after the reaction. Okay, so this is the number of moles of acid that had reacted with calcium carbonate. Once we have found that, we can then compare mole ratio again to find the number of moles of calcium carbonate. But take note over here, Now we are looking at the reaction of hydrochloric acid with calcium carbonate. So the ratio as shown in the equation 2 is 2:1. So the number of moles of calcium carbonate is actually half the number of moles of hydrochloric acid. Once we have found the number of moles of calcium carbonate, we can find the mass of calcium carbonate and then the percentage by mass of calcium carbonate in the eggshell. Now this is another example of a back titration question. So once again, there are three reagents, A, B and C. The first reagent is your iron hydroxide, okay, but we don't know what is the value of N, so we have no idea whether it's iron 2 or iron 3 hydroxide. Reagent B is your hydrochloric acid and reagent C is your sodium hydroxide. Okay, before we even go on, if you read the question, I hope you can see this part, a 25 centimeter cube aliquot of solution F. What does aliquot means? It means a sample. So over here, you need to, that there is sampling involved. Okay, so once we have identified all that, let's start from, let's work backwards again. We can first find the number of moles of reagent 3, which is number of moles of sodium hydroxide. By comparing mole ratio, we can find number of moles of hydrochloric acid that's remaining. Now, since there's sampling, this number of moles of hydrochloric acid remaining is only present in that 25 centimeter cube aliquot of solution F. So in order to find the total number of moles of acid remaining, we need to use the sampling formula, all right, where we take the total volume divided by the volume of the sample times the number of moles in the sample. So that will give us the total volume of HCl that was present after the reaction with iron hydroxide. Next, we need to find the number of moles of acid that had reacted with iron hydroxide. So how do we do that? Is to take the total number of moles, which is given in the question, minus the number of moles of acid that's remaining. Okay, and then we will arrive at the number of moles of acid that had reacted with the iron hydroxide. Now, some students may be stuck at this point in time, reason being, since we don't know the value of N, okay, there's no way for us to compare mole ratio easily. But if you were to construct the equation, this is what you will get. All right. So the number of moles of iron hydroxide is actually equal to the number of moles of acid divided by N. Okay. And then since the mass of iron hydroxide is given, we can also write another equation in terms of N for the number of moles, which is mass over your molar mass. Now that we have two equations for the number of moles of iron hydroxide in terms of N, we can actually equate them and solve for N, which will give us a value of 3. Okay, that means that the iron hydroxide that we are looking at in this question is iron 3 hydroxide. Now the next type of question that we're going to look at is known as a double indicator titration. In a conventional titration, we only make use of one indicator and we stop titrating when the indicator changes color. That is the end point, and we note the titer value. All right. However, in reactions where it involves either a dibasic acid or a dibasic alkali, we have seen in O levels that for a dibasic acid or dibasic alkali, there are essentially two endpoints. Why? Because the acids or the alkalis will react in a stepwise fashion. All right, so there will be two endpoints, and the two endpoints will be at slightly different pHs. Another concept that we have encountered briefly in the O-level syllabus is that different indicators would change color at different pH values. So with that in mind, the use of a certain indicator can actually be used to detect either the first endpoint or the second endpoint in the titration of a dibasic acid or a dibasic alkali. So in this, in a double indicator titration, we actually perform a titration until the first indicator changes color, and then we subsequently add a different indicator until the second indicator changes color, or we can perform a titration with the first indicator to find the endpoint, and we perform a brand new titration with the second indicator and to find the second endpoint. And by comparing the different titer values, we can actually determine, we can actually solve a variety of questions known as your double indicator titration. Now, to solve double indicator titration, there are two very important concepts. The first important concept is that you need to know which endpoint can each indicator detect. But no worries, in a double indicator question, the standard dibasic alkali that we use is sodium carbonate. So when sodium carbonate reacts with an acid, for example hydrochloric acid, it will react in two stages leading to two endpoints. The first endpoint is when all your sodium carbonate has been converted to sodium hydrogen carbonate, and the second endpoint is where all your sodium hydrogen carbonate has been converted to sodium chloride and carbon dioxide and water. Okay, so there are two endpoints. Now take note that if you are using methyl orange as the indicator, methyl orange, when it changes color, it would have detected the second endpoint already. So meaning all your sodium carbonate has already been converted to sodium chloride. If we are using phenolphthalein, when phenolphthalein changes color, phenolphthalein will indicate the first endpoint only. All right, meaning when phenolphthalein changes color, it means that all your sodium carbonate has been converted to sodium hydrogen carbonate. Another useful concept is this: when you react a strong acid with a strong alkali, the choice of indicator doesn't matter. Both indicators would indicate the endpoint for the reaction. Now, as for why is the pH of the two different endpoints different and why are the pHs at the particular range, we will learn it in ionic equilibria, where we learn about acid-base equilibria as well as salts. Okay, but for now, the second important concept to take note is this. Recall we mentioned that the dibasic alkali sodium carbonate will react stepwise, so it will undergo two reactions which will give rise to two endpoints. This is the first endpoint and this is the second endpoint. Now imagine this: if I have 0.1 mole of sodium carbonate to start with, when all my 0.1 mole sodium carbonate has been reacted in reaction 1, what would be the number of moles of sodium hydrogen carbonate formed? It would be 0.1 mole. Okay, so the number of moles of sodium hydrogen carbonate in a double indicator titration is always equal to the number of moles of sodium carbonate. This is one important concept to remember. The more important concept is this: if I have 0.1 mole of sodium carbonate, it will essentially require 0.1 mole of hydrochloric acid to reach the endpoint or to reach the equivalence point, and that will produce 0.1 mole of sodium hydrogen carbonate, which will again require the same number of moles of acid for reaction, for complete reaction. So what that means is that the volume to reach endpoint 1 is equal to the volume from endpoint 1 to endpoint 2. So the volumes of acid required to react away your sodium carbonate is equal to the volume of acid required to react away your sodium hydrogen carbonate, or V1 equals to V2. Now this can be seen in the titration curve as well, you can see that at the first endpoint, the volume of acid is as follows, and from the first endpoint to the second endpoint, the volume is the same. So just a quick recap for double indicator titrations, you need to remember two things. You need to remember number one, that phenolphthalein will detect endpoint 1, methyl orange will detect endpoint 2. Second thing to remember is that the volume at endpoint 1 is equals to the volume of acid required from endpoint 1 to endpoint 2. So let's make use of these two concepts and apply it to this question. In this question, we have a solution containing two alkalides, sodium hydroxide and sodium carbonate. Okay, so this mixture of alkalides required 19.2 centimeter cube of acid with phenolphthalein as the indicator. Okay, so since we are using phenolphthalein, remember sodium hydroxide, it doesn't matter because it's a strong alkali. For sodium carbonate, when you're using phenolphthalein as the indicator, remember it will only detect the first endpoint. That means it will only be reacted to form sodium hydrogen carbonate. Okay, so in the second sentence, we added a second indicator, which is methyl orange, and a further 5.1 centimeter cube of acid was required to reach the endpoint for methyl orange. So this 5.1, right, if you can recall again that methyl orange would detect endpoint 2 and a further 5.1 centimeter cube. So what is this acid, this 5.1 centimeter cube of acid doing is to convert your sodium hydrogen carbonate to sodium chloride. So essentially, in the concept of V1 and V2, this represents a V2. Okay, a further. So 5.1 centimeter cube of acid is further required to convert your sodium hydrogen carbonate to sodium chloride. Then in the second concept that I was mentioning earlier, that V1 is actually equals to V2. Right, so what does that mean? It means that out of this 19.2 centimeter cube of acid that had reacted with both sodium hydroxide and sodium carbonate, actually 5.1 centimeter cube actually reacted with your sodium carbonate, and the remaining must have reacted with your sodium hydroxide. So once you have gotten all these volumes out, the rest is pretty simple. Okay, so as mentioned, the volume of acid that had reacted with sodium hydroxide is 19.2 minus 5.1. So this 14.1 centimeter cube of acid actually reacted with sodium hydroxide. With that, we can easily find the concentration of sodium hydroxide. Okay, and then next, we know that we can find number of moles of sodium hydrogen carbonate by taking the volume V2 times the concentration. And remember, the number of moles of sodium hydrogen carbonate is actually equals to the number of moles of sodium carbonate. And once we find the number of moles of sodium carbonate, we can just divide by the volume again to find the concentration. Here is another double indicator question. So we have a solution containing again sodium hydroxide and sodium carbonate, and then it required 21 centimeter cube of acid with phenolphthalein as the indicator. So once again, detect concept number one, that phenolphthalein as an indicator would only detect endpoint 1, where we convert sodium carbonate into sodium hydrogen carbonate. Okay, the next part tells you this, that we did a brand new titration with methyl orange as the indicator. So now when you use methyl orange as the indicator, the endpoint is this. So when you use methyl orange as the indicator, remember that your sodium carbonate will be fully reacted to sodium chloride. So it will detect endpoint 2. Okay, so with that in mind, when we compare the two titer values, the difference of the two titer values would actually tell you the additional amount that's required to convert, or the volume between endpoint 1 and endpoint 2. Okay, so earlier we have abbreviated this volume as a V2. So the difference between the titer values for the two experiments, the two titrations, will give us the value of V2. And once we find the value of V2, remember V2 is equals to V1, okay, and 21 centimeter cube represents the V1 plus the volume of acid that had reacted with sodium hydroxide. So once again, 21 minus a V2 or V1 would give you the volume of acid that had reacted with sodium hydroxide. And once again, after finding the volumes, it's very simple for you to therefore find the concentration of sodium hydroxide and sodium carbonate. Now in this question, they required you to leave your concentration in grams per dm cube. So it involves this additional concept that we have learned in O-levels, where mole per dm cube, to convert mole per dm cube to grams per dm cube, essentially we multiply by the molar mass. Here is one last double indicator question. So this question is slightly more tricky because we have a mixture of sodium carbonate and sodium hydrogen carbonate. Okay, so sodium carbonate is contaminated with some sodium hydrogen carbonate. Okay, and then 25 centimeter cube of this solution required 11.2 centimeter cube of acid with phenolphthalein as the indicator. Okay, so remember, when you use phenolphthalein as the indicator, it can only detect endpoint 1. Okay, meaning your hydrogen carbonate impurities will not undergo any reaction. It is not detected by phenolphthalein. Right? And then when you perform a second titration with methyl orange will detect the second endpoint. So this final titer value, the second titer value, will represent the volume of acid required to react your sodium carbonate all the way to endpoint 2. It also includes the volume of acid required to react with your sodium hydrogen carbonate impurities. So as discussed earlier, I hope you can see that 11.2, so the endpoint with phenolphthalein, would therefore represent V1. Okay, and we have learned that V1 is equals to V2. Okay, so to find the volume of acid reacted with your sodium hydrogen carbonate impurities, we would take the total titer value minus 2 times of V1 or 2 times of V2. Why? Because with methyl orange as the indicator, your sodium carbonate will undergo the 2-step reaction completely. All right, and each step requires 11.2 centimeter cube of acid. And once again, that will give us the volume of acid that had reacted with your sodium hydrogen carbonate impurities. And once we have obtained the volumes, once again, it's easy for us to find the number of moles of your impurities, the mass of your impurities, the number of moles of your sodium carbonate, all right, and the mass of your sodium carbonate, and lastly, therefore, the percentage by mass of your sodium hydrogen carbonate impurities in the mixture.